classical error correction codes? Well, basically, it's because classical error correction codes, they take into classical mechanics principles, and quantum error correction codes are basically for quantum systems, because classical error correction codes do not work based on the principles of quantum mechanics. So, what are these differences, and why do we need the quantum error correction codes? So, the first thing is that measurement destroys superposition. So, as we know, like a qubit is a superposition of the zero basis state and the one basis state. And when we measure this particular qubit, the superposition which is there, it is destroyed because the state collapses either to zero or one. So that's why we cannot use classical error correction codes, because in certain decoding algorithms, there are we'll have to know what exactly the value of the received received bits are. While in quantum, we cannot do that because we cannot measure the code word, because it will destroy the code word. And the next thing is other no-go theorems of quantum information theory, like the no cloning theorem, no broadcast theorem, and various other theorems, due to which we cannot copy the same state. So we cannot copy the same quantum information and parallelly process them. And the third one is that quantum errors are continuous. So, like in the classical case, we just have bit flip errors, like zero is flipped to one, or if you have something in the higher dimensional field, it's just changed. It's just a symbol change. But in the quantum case, because errors are continuous, they basically belong to something called as the unitary group. So, because of this continuity of, because the errors are continuous, hence we cannot use the classical codes directly. We need something which deals with this continuous errors. And we actually kind of digitize them by using some basis operators and stuff. But even there, we have to deal with two types of errors. One is the bit flip error, which is very similar to the classical error correction code. But there's also one more type of error called as the phase errors, because phases are involved out here. And we'll have to kind of correct the error, both of these errors simultaneously. And that's why we can classical error correction codes. So, but because of the similarity, there is the framework of codes which are basically used for quantum codes. They're that's called as the stabilizer framework. It is analogous to the classical additive. There is some relation between the classical additive codes and the quantum codes that are built using the stabilizer framework. Although it's not trivial, it is a non-trivial process. So next, I'll be speaking about like what are the prerequisites that are required for one to pursue research or study about quantum error correction codes. So the first thing is about the stabilizer framework. So all the known quantum error correction codes, they're constructed or based on stabilizer framework. So for this particular framework, we need linear algebra basics, which is like common to everything in quantum. Because quantum dynamics is linear. We also need probability basics, because here we're speaking about quantum error correction codes. So quantum information theory comes into play, and we are building these codes for quantum channels, let them be in quantum computers, communication, or storage channels. And we have to look into the we need to we need reliable we need we need to reliably correct the errors. So that's why we need probability basics. And we need quantum mechanics postulates, because whenever we are building any circuit, or whenever we are doing any processes, or building any theories, we need to abide by these quantum mechanics postulates. We also need abstract algebra like finite fields, groups, and rings to build our codes. We need quantum states and operators, because at the end of the day, that's what we are trying to encode. And basically the quantum states are basically how we represent the quantum systems, and operators is basically defining the processes that operate on these quantum systems. And we need quantum information theory. Next is about constructing and the entire theory and the code properties of these codes, which need linear algebra basics. We also need probability basics here, and abstract algebra. These two things basically need modules 1 and 2 of the course. And the third is about the code construction algorithm, the encoding and decoding, and the error correction algorithms, and also the circuit architectures, about how we can go about building these once using all the quantum technologies which various physicists are working on. So we need linear algebra for that, probability, quantum mechanics postulate again, abstract algebra, quantum states and operators. We also need a knowledge of quantum gates and circuits to know how do we actually go about building these circuits. And we need complexity analysis basics, because we need to build the most efficient possible circuit for these, and also order analysis of these algorithms. So we need modules 1, 2, and 3 of the course. And module 4 is not directly related, but having a knowledge of all the quantum computing algorithms is very helpful for improving the efficiency of these algorithms, because it gives an idea of how we can use superposition and entanglement to our benefit to improve the efficiency of the codes. So I would like to request Ankur to next take over from here.
Thank you, Priya. Yeah, so there is this growing interest in quantum networks, because there are people who are working in different technologies, right? Some of them are working in superconducting qubits. Some of them are doing quantum dots, photonics. So there is a large interest that how do we connect all these technologies. So that is where quantum networks is going to come in the future, where where we'll have a network links between various technologies in order to make sure that we have a large network, and every node is doing some processing at their local node in terms of the technology that they're using. So this will involve long distance communication, will involve quantum repeaters, because the information has to be communicated from one area to another area. So there will be these quantum repeaters, and we will have to use the knowledge of quantum error correction at those quantum repeaters, so that information can be pumped forward and can be used to connect different nodes in a network. And there is a lot of people, a lot of researchers are working towards enabling or seeing the day, or seeing the light for quantum internet. So that is one exciting area which I am also closely following, and how will this happen in the future. Can we go to the next slide? Yeah, so as I said, entanglement is one of the most important resources in quantum information processing. So when we start with the Bell pair, it's exciting because it's one of the application, as Professor Arun said, was the creation of secret keys. Now this was what he shared was between only two parties. Now if this entanglement is shared between many parties, many systems, then it leads to very interesting scenarios. And some of the PhD work that was done was based on entanglement sharing between various nodes. And there is something called a graph state, and graph states, cluster states, and there are so many things that happen when the entanglement is shared between various systems. So some of the models that exist for quantum computation is this quantum gate error model, which is basically a unit. If you want to perform a certain unit operation, so in the quantum world, you inevitably are going to do unitary transformation. So this unitary transformation, how do we enable? So there are various ways in which these unitary transformations can be created. So one of them is the quantum gate error model. So you have basically a state, and then you have some ancilla qubits. So you basically do some connections between these, and you propagate the information, and in the end what you will have is a unitary acting on the initial state that you started with. And so these are all actually there are four currently. What people have found is these four ways of performing quantum computation. Measurement based quantum computation is basically, again, it's sort of a distributed distribution of entanglement between various nodes. So what they will do is there will be an initial resource state, and then they will do a measurement on various qubits, and then the information will sort of propagate from one end to the other end. And in the end, what you'll have is a unitary operation performed on the initial qubit. Then there is this adiabatic quantum computing, which is based on quantum annealing, where a quantum computation is like seen as a slow transformation slow continuous transformation from an initial Hamiltonian to the final Hamiltonian, where the ground states contain the solution. There is this interest in topological quantum computing, where it's based on braiding of anions. And so there is this famous paper by Alexei Kitaev. So you can check this out. This is, and as far as quantum error correction is concerned, there is this surface codes which are widely researched upon, and this is like one of the very upcoming fields in quantum error correction, which are the surface codes based on the topological quantum computation. So this is something which is happening in the research at various places. Can we go to the next slide? Yeah, so why do we need quantum algorithms? There is this question, and there were some of the algorithms that come is we will share them in the next slide. So there is this speed up of problem solving is possible using parallel processing due to superposition principle. For example, you have in the classical, what you would do is, if there is a function that you're doing a computation, what you will do is you'll input x, and then you will get f of x, right? And you will build this entire table. For every x, you will get an f of x, right? So in quantum, what is possible is this superposition principle. So quantum states exist in a superposition of various basis states, and if a function is there which computes these f of x for every possible x, what you can do is all of this can be in a superposition. So instead of doing in a serial way where you will do one input and another output followed by input followed by output, and you will build this entire body this circuitry, what will happen is all of this is going to happen in parallel, and that provides a speed up in solving some of the problems. And there are in the current literature, what is happening is they want to speed up whatever classical problems are there. They want to find a quantum solution, and is there a possibility that you can speed up in terms of computational complexity if you are using. And there have been solutions where there are exponential there is exponential advantage. You will reduce the number of computations exponentially there, and there are some of the solutions are where you are you're having polynomial advantages. So this is very exciting area where one can pursue quantum algorithms to see some of the problems that are unsolved in classical world, and there are some of the problems that can be speeded up using quantum computation. And some of the algorithms are, you can check it up, you can learn it. Some of the well-known are Bernstein-Vazirani algorithm, Simon's algorithm, Grover's algorithm, Josa-Deutsch algorithm, and of course the famous Shor's algorithm. So you can check these algorithms, what they do, what kind of problem statement is, and how a quantum computer can be used to speed up these solutions. So the interesting part is, like, can we use quantum algorithms for all problems? Can we just completely replace classical? I think as far as my understanding is concerned, I would say no. Like, only certain problems which have a certain structure, quantum computers can use the structure and can efficiently speed up the solution. So, and there's going to be a bridge. There are certain problems which you can use the classical computer for, and there are certain problems for which you will use the quantum computer. They have to go hand in hand. So you cannot get rid of one or the other. If you want to see this future of computing, you will have to use both of them. And the next slide. So for this, like many students, they get scared. Where should I pursue? What should I do? Actually, you can start with simple linear algebra and the knowledge of Hilbert spaces, basic probability, and basis of quantum mechanics. Like, I came from an information electrical engineering background, and when I entered, even I was like, I was scared. Like, how do I enter into this area? So what one has to do is actually a determined, committed mind, where you can just pursue whatever. You can start with a Nielsen and Chuang book, and you go with it, and you enter the field. You understand and what's happening in how is the concept being explained, why are we doing a certain task, and using simple techniques like of these basic probability and Hilbert spaces, you can actually enter the field. And once you feel a little bit more confident, you can explore other areas as well. So I think it's an exciting field, and we are all geared up to see how this will see the future. Thank you.
Right, should I take over from here?
Yeah.
Right. Right. Hello, everyone. Thanks for joining today, and it's a pleasure to be in this talk, which has looked at various aspects of quantum information theory. Today, I will be talking on quantum resource theories and hyperentanglement. So probably I'm a slightly the odd one out here because my background has been primarily physics all through, and I have been looking at currently as a postdoc at TIFR. I'm looking at Majorana fermions and topological quantum computing systems, which are realized in certain physical platforms. And I have also been looking at, previously I've been looking at quantum information processing tasks, such as teleportation, quantum communication, and cryptography. So here I would like to put forward what I see as the primary kind of central element when it comes to the whole discussion on quantum information and entanglement, which is to do with the whole idea of resource, right? I mean, it's a very simple word. What is a resource? So when we're talking about quantum information processing, there are some tasks that need to be done. I mean, in terms of protocols and in terms of realization of certain things, which I will be discussing. And there are in physics, we have the idea of symmetries and constraints. And given a certain symmetry and a certain constraint, or a set of symmetries and constraints, one can have a useful physical resource, so to say, which one can utilize for various tasks. So if I could go to the next slide, please. Right. So, I mean, what defines a resource, right? I mean, what is a resource? A resource theory, for a given, setting is basically categorization and characterization of actions in being either free or prohibited. And the idea here is, if we go back to the early 20th century, this is a brief bit of a historical tidbit. In 1894, Michelson, the famous Michelson-Morley experiment pioneer, said that physics, it's a longer quote, but he says that physics has been determined up to, only the fixation of certain decimal points, or the fixing of certain decimal points. And most of it is generally kind of known, right? And obviously in a decade or so, there was a complete overhaul of physics. And we had the Annus Mirabilis in 1905, where Einstein came forward with 4 seminal papers in various areas of physics. Now, in that respect, even relativity for that matter, put forward newer ideas of space-time, for instance, and the dynamics that can take place given that formalism. So for that in that area, that was the constraint, and therefore thereby we could define dynamics with respect to the reset resource, so to say, in that picture. The basic idea for quantum resource theory is to study the information processing under a restricted set of physical operations. One can look even beyond to look at things like, for instance, channels and how they have certain inherent constraints. People have spoken about decoherence as well previously. So one can look at how to protect the resource from decoherence in what is known as decoherence-free subspaces, for instance, which has also been an area of interest for myself. And so this is a very key point, which is to look at how we can have a resource theoretic outlook to the study of quantum system, since decoherence and other such processes can rapidly eliminate the quantumness of the system. And the most well-known theory of quantum resource theory, so to say, is that of entanglement. There are other kinds of correlations. There are ideas such as discord, which can also be looked at. And so for 2 or more quantum systems, entanglement can be characterized as a resource that when the allowed dynamics are a local, quantum operations, and classical communication, which is LOCC. What I mean by that is, that we have this constraint that if there are, let's say, many terminals in a quantum network, they can only locally apply certain operations to perform some transformations, for instance, and they have access to classical communication channels, which they can have access to as well. So under those constraints, what is optimally the resource that goes beyond just that is what the entanglement picture brings to the fore. The entanglement is the resource that can be utilized such that we can have various quantum information tasks, which when supplemented with LOCC can give us very useful and optimal processes and protocols that can be utilized. So could I go to the next slide, please? Right. I mean, so why are quantum resource theories important? So there are a few, 4 points rather. So they obviously have a practical perspective. They provide a practical perspective as to what are the quantum operations that reflect these experimental capabilities. So if you have to perform certain kinds of, let's say, protocols, let's say an algorithm, one has to kind of, much like in when you have to look at distances and how to kind of look at what are the distances between 2 points on, let's say, a sphere, or there is this whole idea of triangulation. Similar to that, one can have a subset of operations that can be together and cumulatively that can give rise to a certain protocol or give rise to a certain application, so to say. So that is where the resource theoretic picture is very important. And I mean, there is obviously characterization of entanglement, which is important. For instance, one has this idea of distance measures. So what one means by that is that one can look at how a certain resource state is optimal or not optimal for a certain specific kind of application. So for instance, one can have things like cluster state quantum computation, which don't quite have maximal entanglement. They have a very interesting form of entanglement, which is, with respect to a certain operator, super operator, tensor product of certain operators. And that is the kind of entanglement resource we need for that kind of a measurement, application. The second important thing is that this provides the foundation to rigorously compare the amount of resource for a particular task. I mean, that is what is most important. And given certain system constraints, what can one get from there? And it obviously enables a fine-grained analysis of what are the fundamental processes and properties that drive a certain phenomena. And lastly, they identify the structures and applications that are common to the resource theories in general. Now, the major things which are, major resource theories that one has looked at in the recent past, obviously one is to do with entanglement. And as I mentioned, there are things like, LOCCs and various other constraints one can put, and with respect to that, one can assess how useful a certain resource, for instance, is. Then there are quantum reference frames and asymmetry, which has to look, which looks at things which are known as fungible resources. Fungible means that which are convertible or changeable to some other resources, and non-fungible resources. So one can have studies on that. There's a famous work by Bartlett in 2007, which was on this. Then there is quantum thermodynamics, which looks at constraints with respect to energy and entropy, for instance, free energy, functionally useful energy for that matter. Coherence, again, going back to the discussion of decoherence and coherence, that's very important. Non-locality, non-Gaussianity, and non-Markovianity, which is to do with order, how ordered or disordered a system is. There are certain things called Markovian kind of dynamics, and you could have things which are slightly more chaotic or disordered, so to say. And then there are quantum correlations, which are not entanglement, but the higher kind of, the bigger, broader family of correlations that are possible in the non-classical quantum picture, so to say. Next slide, please. Yeah. So now I have been working for the last year or so on a very specific kind of resource, basically, which has to do with entanglement across multiple degrees of freedom. Now, this is something which and this is, to give you an example, light, for instance, has multiple degrees of freedom, such as polarization, orbital angular momentum, path-based degree of freedom as well. And it's very interesting that for certain kinds of circuits or certain kinds of apparatus, physically speaking, one can selectively access or transform or do certain operations in each of these degrees of freedom, such that they are kind of protected from each other. So you can have, let's say, a separable state for one of the degrees of freedom and an entangled one for another, or you could have multiple degrees of freedom across the various degrees of freedom, or you could also have a hybrid entanglement where there is the entanglement is cutting across the degrees, so to say. So there are three cases. One is where you have separable, where it doesn't, like, you could have one which is totally non-entangled, and in the other degree of freedom you have a completely entangled state. You could also have a system where you have maximally entangled and maximally entangled or partially entangled states on both the degrees of freedom, or you could have one where both are interconnected and the entanglement is across the degrees of freedom, so to say. And so this is a very promising resource in quantum information processing, particularly to do with optical systems, for instance, and that has been my area of focus. I have been working previously with PRL laboratory with Shayan and Professor R.P. Singh as well. And we have particularly looked at these things called quantum hyperconditional gates. So if you have a certain subsystem which has a certain state, depending on what that state is, what are the things that one can do on the rest of the system, so to say, or the other subsystems, so to say, across the degrees of freedom. So it's not only in, let's say, polarization or orbital angular momentum, but cutting across the degrees of freedom. That is what is known as the hyperconditional gates. And my area of focus has been on that. So in terms of what can be covered and what I would like to cover in this front, I think it has to do with general introduction to hyperentanglement, of course. Illustrative example with circuitry. I have not shown circuit here per se, apparatus, but there are things like nonlinear optical systems where you have this thing called spontaneous parametric down conversion. Basically, it is a crystal. You have a crystal, and you can impinge pump photons into the crystal. And what happens is that you have emitted photons, which are of a slightly lower energy, but they have extremely interesting correlation patterns. So for instance, in terms of momentum or in terms of polarization, there are very interesting patterns that can emerge. And this is one of the standard ways to actually in actual laboratories produce entangled particles, like entangled photons. So this has been our area of focus. But as Shayan was mentioning previously, there is a loss factor which is extremely large. These nonlinear optical systems have almost 10 to the power 6 in the SPDC case. And then there is another element called SHG, which also has a 10 to the power 4 loss factor. So there is a lot of optical gain elements that need to be introduced in certain such experiments, so to say. And lastly, obviously, I would like to look at what has been my area of interest, which is hyperconditional gates and quantum information processing using this kind of a resource theory, so to say. Next slide, please. Right. So, I mean, these two broad areas, which have given a very brief idea about what are the basic things which are prerequisites for both of them. Regardless of which area of quantum physics and information processing you take, I think linear algebra basics and fundamental quantum mechanics are obviously very important. For quantum resource theory, quantum operators and information theory is important. Particularly entanglement characterization is important because one has to look at the kinds of constraints and the kind of applications that can be done. So particularly trace distance and norm-based measures are important on that front. In the mathematical picture, you have basic representation theory and group theory. Sorry. And tensor products and basic set theory and basic thermodynamics. Thermodynamics more because it's just an example of quantum resource theory. That's not as important, but the rest of it has more to do with the mathematical foundation of what needs to be looked at. For hyperentanglement, we have fundamental quantum mechanics again. But here, obviously, if one were to look at the illustrative example, one has to have a slight idea about quantum optics. And that is what I would like to explore further if I do look into this topic, particularly looking at nonlinear optics and linear optical systems and how they can provide a hyperentangled or a hybrid entangled state, so to say. Yeah, thank you.
Thanks, Mrittunjoy. Yeah, Shayan, Professor Shayan.
Okay, so I think you people might have gotten an idea about this whole field, sort of a bird's eye view, I would say. So this is really interdisciplinary, and of course we would like to strengthen the basics from scratch, essentially starting with basic math, basic basic in the sense basics of linear algebra, probability, foundations into quantum mechanics, complexity, etc. That would be sort of module 1. Then module 2 would be on quantum states, operators, and some of these notions there, locality, non-locality, etc., etc. And module 3 would be into circuits, and gates and circuits. Module 4 would be into algorithms and stuff. So it would have a melange of all of these topics, but one feeding into the other. And I expect all of these would be couched within a 30-hour module, something like NPTEL. And but of course it would be modular. 10 we could even have a 10-hour module, modules of 10 hours, and this could just finally one could do a 30-hour module which comprise of all these comprising of these modules 1, 2, and 3, and so on, 10-hour modules. So this is the intent. And these, it would be online, and you would have videos, lecture notes, and resources that people can access. And what I would, of course, we would also gauge your prerequisites before you're ready to take this or not. I mean, if somebody is really behind linear algebra or something, or basic math, then I think you may want to basically strengthen those aspects and take this course. So I think we would do our homework like the way we have done NPTEL courses successfully in the past. So this is how it would evolve. And of course, it's a new field, new area. There is always some uncertainty when somebody wants to register to a course, etc. But be rest assured, you will find this journey fascinating and interesting, and you would not be afraid at the end of it. So this is what I would like to mention here. But I think this is very important because without the know-how, it's difficult to do any research, or possibly, you'll have to, basically self-learn and do things. And here, I think we will be able to put everything together into a perspective and provide the right direction for people to basically pick up on things and go further deep into the tasks that they're interested in. Okay, so with this, I will leave the floor open for questions and answers, discussions. So all of us would be here, and and we can take up questions.
Sure, Professor. So we have received a couple of questions in the chat box, which I was picking it up, and I will pick up one question, which is, there is a class of intellect according to the quantum computers, can never replace classical computers because in reality, quantum algos are much slower than classical algos. What are your views on quantum computer taking on classical computers?
I'm sort of puzzled with the second part. That is, the quantum computers are slower than classical computers. Well, the current state of technology seems to be like that, possibly because you're dealing with smaller number of qubits. Maybe you don't have like great amount of resources, etc., and then you're bottlenecked in your communication processes, etc. But I really don't see that as a bottleneck as such. The bottleneck would be your superluminal communications, because you can't beat the speed of light. That is the bottleneck. Otherwise, I don't see this as a bottleneck at all. As my friends, they mentioned, you're bounded by, you could do superposition, you could do a lot of things in very fast. It's not a bottleneck. But as I think Ankur mentioned, there are certain problems which wherein the quantum paradigm naturally fits in. Like, for example, if you're thinking about artificial intelligence and some of these type of algorithms and implementations, if you go deep down to the level of devices that have to work to enable AI, memory stores and some of these elements, circuit elements, naturally fit into that framework of doing artificial intelligence. So it's really the handle and delete problem, how you would want to kind of see through, right? For some things which are actually you can do, on classical, you don't need to bring in a powerful tool, because the real power with quantum is entanglement, and for which you need these resources, these bell pairs, or multipartite entangled pairs. And this is a resource, and that resource is costly. May not be today, but 50 years later or 100 years later, maybe people will have more efficient solutions where it will be like what we have today. But today it is a costly resource. As you have a factor of 10 power 10 off in your efficiencies and stuff to get, you need to bring those efficiencies back to realize the power of entanglement. So therefore, I think you cannot say it is it may be slow as on today, because you can't, there you're limited by your dead times of your detectors, your EPR generation process, etc., dot dot dot. But the theory and everything is flexible. That's where research has to be enabled, because you need materials, you need that work with these systems and everything else around that infrastructure. So there are, it really, you cannot take a binary decision saying that it is slow, therefore quantum computers cannot be used, or quantum communication. Otherwise, why would the rest of the world be working on this if they knew that you could not do this, right? So if any others in my panel, Ankur, Mrittunjoy, Priya, if you, or Arun, is he here? I think he must have left possibly. I do not know. So if you have any anything to add, feel free. Yeah. So I hope it addresses your question.
Okay. While we have a lot of questions from the students fraternity here, asking which is the best institute for taking PhD, what is their path to get into quantum computing, quantum information, which institution they should take to do PhD, what line they should get in to get more involved in the education or learn the quantum world, right? Quantum information processing. So I'm clubbing 4 or 5
Maybe,
questions put together from various
okay.
students here.
So let me answer briefly, and then I will let the students and the postdocs talk about it because they are better judges. See, when it comes to institution specific questions, of course, one is think globally, again, the best institutions across the world, and also best institutions across India. And of course, there are no isolations as well, because there are connections between institutions in India and institutions across the world. And it's a, we collaborate. So there is really no, it's a hard question to put. And of course, we look at the ratings from, these, Times Higher Education rankings, or your US News rankings, or higher ed rankings, etc., and you get a certain impression, and you have an opinion and biased. So I really, this is not, I mean, this is of course a routine way of looking things. But really, I don't think this is the way I would look into. I really go with the old school of thought. I look at the professor who is working in these areas. What's happening exciting there, what new can I get from these, and this is how I would make my decision for higher education. For undergraduate, it's fine. You can just go like herd mentality, right? Even masters, you can go with a herd mentality. But particularly with PhDs and postdocs, I think it is very specific to the professor, to the group, and things, the team and stuff like that. And that's very critical. And that's what one has to really look into. And I would say I really like students who actually start with nothing and build things, rather than something which is already there and then you just say it's available. I mean, the journey is always when you create things. Of course, that's the reason why you get a PhD, right? So I think I will basically leave this perspective, talk about it from this perspective, from my postdocs, and from my PhD students, and they would be able to tell you their perspectives as to what they think, quote unquote, which school is important. Of course, I as a professor would advocate IASC because I come from this institution. So therefore, I would advocate IASC. So come and join IASC. And also, it's a pitamaha of the Indian institutions. And I would say people. Of course, we are not so well marketed compared to IITs. When people, this is always the situation. They say, yeah, IITs we know, and many times I would have to intervene there and say, IIT IITs were fathered by IAC. So and the famous names of the Raman or the Sarabhais and all these things, when when you dot when you bring it into the list, that all came from IAC, or even the ones that are active today, leading researchers. So somehow it has not been marketed to the way it should be, but people in the scientific community know very well. When they talk about Indian Institute of Science, they know about it, and the contributions from of IAC, 110 plus years, dating back even to the pre-independence time, and the mission and the goals. But since it's been predominantly, and it is to a very large extent, 98% is predominantly graduate focused, graduate level focused, PhD, masters, PhDs, postdocs, master students, and not the undergrads. So we have not produced so many undergrads across, or so many alumni across that that have spread that kind of thing forward. But a lot of very high quality work has happened from Indian Institute of Science. So I would advocate, but from Indian context. And there are also, of course, excellent IITs and faculties working in IITs, TIFR, etc., leading institutions, and even local universities, Harishchandra Institute, for example, HRI. So I would not really bias. So you have the Ashok Sens, you have many people around the country. So you figure out, just go through the websites, you figure out the individual faculties, and you figure out what you like to work on. But of course, I can tell you, IAC has the infrastructure to catch all of you, because it is multidisciplinary from engineering to sciences. We have everything around, and therefore you are free to basically work on things. And this is what I would like to advocate. But of course, I would like to pass this question to the student, to my PhD students who graduated, and Mrittunjoy, who is interested in joining ISC, who would be joining ISC sometime very soon, who is now a postdoc with TIFR and a PhD from Cambridge. He should tell his perspectives, and Ankur and Priya should talk about their experiences. So I will leave the floor to them.
Right. Should I? Okay. Right. I mean, so this is a very interesting question, because obviously at what point and how much can you engage with it? I think for myself, it was from my undergrad days that I was, into quantum information processing, because I got a TIF or NIUS fellowship. So as part of that, I could look into certain aspects. So I would suggest that even at that level, even at the undergrad level, be it within the university or institution, or even without, there are some opportunities, quite a few opportunities these days. One should make the best use of that. If there are internships, if there are some research experiences, that helps a lot, particularly with respect to very good master's or PhD level programs as well later on, if you want to go in that direction. With regards to where PhD can be done well, I mean, there are obviously lots of universities in the world. I mean, in the US, there are quite a few universities. Cambridge has been doing quite well in certain areas of quantum information processing. There are universities in India, as Professor Shayan rightly mentioned, very, very good universities, RRI, HRI, ISC, of course, and Australia as well. So there are lots of places. But the key point here, which also Professor Shayan mentioned, is that the area within quantum information that you want to look at. So obviously there are things like mathematical aspects of quantum information, the foundation, so to say. There are groups in ET at Zurich and various other places. Even in India, you will have HRI and various other places where it's very good. Then you will have a realization in optical systems or other kinds of condensed matter systems, where let's say EPFL in Europe or certain other universities will be better off, right? So there are certain professors who are looking into those subjects within the quantum information domain. So I think it's very important to look at what particularly interests you and have a very targeted approach towards looking at the group, the professor, and the good work that's been done there in that group, and move in that direction, rather than just having a brand or a tag related kind of a drive, essentially, at least in the PhD level. Yeah.
Yeah, Priya and Ankur, you would want to also add this?
I think most of it was covered. I would say just going with the passion with what the student is passionate about. There's so much in the field. Within the field, there are subfields, and one can pursue that. If one is very mathematically minded, there are so many unsolved problems one can look at. One, if one is interested in experiments, then checking the lab of the professor, how is the resources there available in the lab, what kind of implementations a particular professor is looking at, and yeah, so these theoretical and the practical aspects one can pursue, and one mainly it's the passion. Actually, if one is passionate about, he can find, and he will find a place where he can pursue that passion.
Okay, how this our course module will help the students identify uh, which path they should take it, right? So can we match it with the module that panel is proposing as well?
Yeah, see, I think this is going to provide a foundation at the senior undergraduate / introductory graduate level. That's the target, right? I mean, many topics were touched upon. For example, you may not need so much of operator algebra or representation theory, etc. It's not also expected possibly, but we'll be covering like this would be like a foundations to quantum information processing, like part level 1 course, which is going to be basics of linear algebra, probability, foundations into quantum mechanics, not in sufficient depth, but possibly 3 to 4 hours of introduction, and then complexity, etc. Some of those basics that would be like part of module 1, possibly for about 8 to 9 hours. Then it's going to get into the details of quantum states, operators, locality, and all of these things which are useful, and that perspective there. And when we touch upon, we'll also talk about the physical perspectives. It's just not like an abstract mathematical object, and you will see the connections from physics to math, and then engineering and technology and stuff like that. So that is how this is going to be structured, and you don't have to worry about it if you do not know what a multidimensional vector is. We'll start with that, and then with a line of introduction, you will know immediately what it means. You can picture that in your head. So that's how it's going to start. Okay, and then and after that, once you understand the what this quantum means, basically the language. First of all, it's a difficult thing for students to understand the language. You see the notations and things like this, you get confused in your mind. And then it all really boils down to basically dissecting these things and then getting that picture. What is it, what is this the symbol, or what is this notation meaning, physically. And once you get that clarity in your head, you will juggle through all the math yourself. You'll be able to do these things with clarity, and that's what we want to emphasize. And from there, we'll get into these quantum gates and circuits. And gates are fundamental. If you have to realize anything, you have to start with these gates. How do we think about it from a mathematical perspective? And then also, what is the physical connection? How do we realize these gates in practice? Things like this. There'll be connections again all the way from math to physics, math to physics, math to physics, and engineering, right? This is going to be how it's going to be woven in together. Then after this, from circuits and gates, we are going to get into algorithms, because now you have all the foundations, and then we'll get into algorithms and realizing these algorithms, how you can kind of build things around that. You can try it out possibly in your quiz kits from IBM, from what is provided with IBM. Or I think this is one thing. Second is, you should not think about what we are on today, like yeah, I have some programming language available or some platform available, I'm going to do this. Well, that gives you one feel, but above and beyond, it should motivate for you to think about deeper problems. That you have to, this is a vision that you have, a high level vision. You want to bring the quantum internet or the quantum computer with all, or quantum memories and stuff like that. That's a dream. How do we get to those dreams starting from scratch? And this is how it would motivate. So don't expect that within a year you're going to get a job, but it's going to happen very soon. Because I think it's going to be, when things pick up, right, I think it really picks up momentum. And I don't think people should be lost out because they don't understand what's happening, right? And this is how we would like to sort of pitch in. So Priya, do you want to add anything to it? I don't think you spoke about.
Yeah, I would want to say like very similar things to what you said, but I would also encourage people to go and speak to the professors, like whom you would want to work with, so that you can get to know if you're really interested in that area, and if you're aligned to the professor. Like even Professor Shayan, he encourages that. So before the PhD interviews and even before applying, you can go and speak to the professor and get to know what exactly the professor is working on and whether you're interested in that area. So in PhD, interest matters more than how much you really know at the start of your PhD, because even for me, like I hardly knew anything about quantum systems in the start. But once I was at IISc, I could pick up things and I could learn it because I had interest in these areas. So that's something which I would like to add.
Sure. So the next question that's very interesting is people talking about how this is very interesting field, and what do you think enough jobs will be available in the next 2 years?
Good question.
Yeah.
Right. Okay. So here is what I would. Okay. It goes to my, I think, first slide. I think when I talk about the synergy between academic research, industrial R&D, society, and governance, and all that. So you have to start somewhere from scratch. So where do you start, right? So this is where it starts with academic research, and then now you have something to start with. And now, from a business perspective, you want to show an order of improvement. For example, when you talk about, let us say, communication using quantum, than without it, you should be able to tell you are able to get remarkable throughputs than what you have as on today. So for you to get remarkable throughputs, like if you think about a fiber optic cable, let me tell you, you may get a gig plus or maybe tens of gig possibly, right, under very high SNR conditions. But now if you want to better that, you have this technology here with quantum that you could potentially do, or very high precision instrumentation, right, that you want to measure something at beyond pico or femto, something like that, which today's instruments, you don't have that kind of precision instrumentation, right? So imagine a photon, one photon, E equals h mu, right? Do your Planck's constant, do your frequency, multiply them, what order that energy is. That hits, and there's a change in your resistance or whatever, and you're interested in bringing these magnetometers or this precision instrumentation. This may have profound applications. So once you show there is some technology, you have to build on top of it. And so I think that is how I would start. That's how I would start. For example, I'll tell you perspectives from magnetic storage. In the 1970s, even 60s and 70s, they had this huge bulky analog equalizers and stuff where you could really see the magnetic grains like this, literally, and you could basically tune the equalizer, and you could really control what you could store. Huge bulky things that you could store one or zero on that grain that you could see through what it is. It was something like that. Maybe even more than a milli scale, but things have evolved from there. Today we are at nanometer scales that you can't. Nothing is just all within a small SD card that is where all your information is, holding terabits of information. And quantum has that potential even below that. So the job creation process has to be evolutionary from research technologies. Once there is some progress, you build technology and show that it is possible. But for that, you have to show that there is some order of magnitude improvement. I think this is all possible with quantum. From precision instrumentation, quantum computing, too, I think, a lot of problems can be because the quantum, this quantum advantage, a lot of these companies were able to demonstrate. Right, Google had some interesting demonstrations. So I think you should look through all those, and I think this is going to pretty much pave the way. But you may ask these questions like, can we get it at room temperatures and stuff like that? That may not be immediate. Superconductivity at room temperatures and stuff like this. These are grand challenges. It may happen not today, but some years down the lane when as things evolve. And any new research that you see solving the problem that is persistent today, that creates a business opportunity. And when there is a business opportunity, it opens up employment, ... This is how I would see things.
Thanks, Prof. So the next question that is there is, there are a lot of courses available through edX, Udemy, and IBM is providing their own courses now through coding school, summer school, etc. So how that is different from the modules that we are presenting in the or you are going to propose these 4 modules, how those are different from them?
Okay. Good question. So this is going to be, I think individual centric than just a mass something that you could see. For example, in NPTEL also, because of, some certain constraints on the number of students here, I think we would like to even target large number of students, 100 plus, possibly there's a cap, like, we can't take more than 200 or something like that. But we would like all these people to come on board. And I think depth and breadth are what we would focus upon, with individual attention to the details that the student has to pick up. And strongly we will encourage projects in the courses. And I think, teaming up or doing individually, we encourage projects. And I think right now we are limited in terms of just being able to do this in terms of software and trying these algorithms and things out, since it's also a foundational course. Hardware is what we really, I think that would be a game changer for all the courses. And I really would like to see this, not today, but I think my dream is in 2 years from today. That, if we are going to pitch it right, we will say that, yeah, please try this on this piece of hardware 2 to 3 years from today. Yeah. So in that sense, it's going to be different. And we want people to get that hands-on experience and individual attention towards doing things. And that's why we have a team of 5 people and a structured way of approaching this thing. I mean, it's not like immediately you're going to build a quantum computer or immediately you're going to launch a magnetometer and you're going to, it's not possible, right? It's not possible. Let me put it honestly. And even those that are working in the AI area, for example, I tell them, come on, can you build the next neuromorphic processor immediately? Building all these memristors and replace them instead of transistors or silicon device, normal CMOS kind of stuff. I don't think that's going to happen. So don't have such expectations, but at least if you dream of such expectations, dream of such things, this is where you're going to start to get to that ladder. And that's what we want to pitch in. And that way, and since it is individual focused, it is going to be different from the mass Coursera or something like that. So we're not going to take too many people, but not too less people. So we admit up to a bandwidth of about 200 people that we would like to cater to all of you.
Okay, there is question like, is there any possibility to conduct experiments in the colleges in India?
That is what is required. That is what is really required, and that mantra should just go out. I am telling, I've been vocal about it for quite some time now, and I think I myself should start. My hands, in the classical side is, I've been in the quantum theory side. In the classical side, we also do the experimental part with FPGA circuits and so on. But yes, quantum side, you really need to do the experiments, like the way one built oscillators, amplifiers, and things like this in the electronic side. This is where we have to start. But it's again a very vast field. Photonics is one vertical, superconducting is another side, NV centers is another side. You can't be a master of everything. It's impossible. My personal interest would be in the area of photonics, and I see some promise there. That what I would like to do, and engage myself in that, and my team as well. But I think you should go. You have to start from somewhere. I mean, otherwise it's going to be inertial state, right? You can clap your hands like this, if from Ampere's law to from Ampere or whatever it is. They did these experiments, or the electric bulb, whatever that Edison had to do to get things right. This is the state where we have to do things. But of course, we are sort of well cushioned, thinking about just our computers and coding, and because we're used to it. Now even a kid, 7-year-old knows what a software code is. They would have possibly seen the compile of a C code hello world, and they can see the output. That is not what I think we should do. We should really set up experiments, for which I think this has to go like a revolution. Everybody should get to do things, but of course this is a niche area. It's not easy to enter just like that. Even for some of us who are seasoned in these things and who've seen through the evolution of some of these areas, it takes a lot of knowledge and then basically a certain leap of faith to enter and be successful at it. So it's not like writing a piece of code and compiling hello world. Certainly not that. It's a very specialized thing. But yes, adoption should start in everywhere. And I don't see much of photonics all over India. And interestingly, the Nobel in physics from India is from Raman, who is very well known and famous for the Raman effect. And somehow I have not seen that takeoff so much in a big time that it should be basically India should have been a leader in the area of photonics, in everything. And so it's, yeah. In general, yes, I think around the world we need experiments along with
So
solid theory.
adding to the same question is will there be any simulators be created or for testing and understanding the concepts? So if there is any
Oh,
math.
there are already very good question. See, for example, I know in IAC, Professor Apurva Patel is thinking about, he already has some simulator setups that he's thinking about. He already has that people are working on these and developing these simulators to exercise a piece of code, software, etc. So you should write an email to Professor Apurva Patel from physics department. He's with you can go do a Google search. You can get the information or let me know. So he's working on the simulators and stuff like this. So to realize algorithms and how you could speed them up, etc., because still you're using the classical objects for these things. Really, the game changer is when you have a quantum hardware, a quantum RAM or a quantum ... whatever that you see, a quantum computer with quantum ingredients, and then sitting on it is a quantum code that you would compile and run on that beast. That is where we want. But yes, you could try the simulators, quantum simulators that still work on classical platforms. I hope it addresses your question.
Yeah. The
But
next
really, we need hardware. This is really the key. Yeah.
Yeah. So the next question is there any cost associated with the course and when it will be available? From when the modules will be available?
So I think my vision is that this would basically come through IASC's Center for Continuing Education, CCE, because that's the only way, that's the only outlet it has to go through. Otherwise, unless there is a paradigm shift in the way we think, with the new education policy, I do not know what can happen or what the government has its vision. I mean, I can't read their mind. So not at least entangled to what they see. So therefore, this has to go through the CCE's umbrella is what I think. And the CCE has the policy. It is 5,000 rupees per credit. So which is going to be 15,000 rupees for 3 credits. And the 1 credit is roughly 10 hours. So it's going to be a 30-hour course would cost 15,000. But I think it would be self-contained, where the videos are available for the course participants. The course notes carefully compiled would be available to all the participants. And that is how this is going to be. This is hopefully going to be launched. And it is, and of course, you may ask NPTEL, because it's not going to be launched immediately through NPTEL, but it can happen as a next step, where it can be launched through NPTEL. And but I think one thing that you should note is with these type of courses, specialized courses through CCE, through ISC, etc., there is a cap on the number of students. Unlike NPTEL, 10,000 students can take a course and the computer can grade the assignments and your exams within no time and provide you a grade. But here, I don't think we are going to go in that mode, because it is humanly impossible to pay individual attention if we go en masse. So there would be a cap, no more than like 200 students, but there would be very carefully crafted homeworks, assignments, etc., and very individual focused that we would like to take, so that we want people to get on board and we want to sail them together with us, so that they are not lost. So therefore, that is the and to come up with these materials sitting down and getting all these things done, there is a cost associated with it, and I think that is something which I think I would like to make a mention here. Yeah. But I do not know exact figures. I think these are the figures. You can check with CCE for these figures, and I think it is
Okay, with this, I would like to conclude here. I would like to thank Professor Shayan and the panel members, Priya, Ankur, Mrittunjoy, and this brings us to the end of this session. If you have any other questions, you can always drop it to us. You can we can talk about it. We can pass on your questions to the professors, and feel free to provide your comments and as well as any feedback to us directly. Thank you.
Okay, thank you all, and it was great to be part of this session. And we thought it'd be done soon, but you engaged exactly for 2 hours, and you know your business, so so I your value for time. So it was a pleasure being here with my team. Yeah, thank you.
Thank you.
Yeah, thank you.
Thank you.
Thank you, everyone. The videos will be sent to you over email, and right now it's on YouTube as well. You guys can check it out. Thank you, Prof. Thank you, Priya, Ankur, Arun, Mrittunjoy as well. Thanks, guys.
Thank you.
Mhm.